Hello everyone, welcome to another session of Meru Butter Talks in Math and Physics. We are very happy to have you all here after a very long time, and in particular today because we have a very special guest, our very own Kazi Fahim Reza Arko. He's a very special student of mine, and we're very proud to have him here talk about his internship work. So the floor is yours.
Thank you. Can everybody hear me at the back? It's clear? Okay. So by the title, you already know it's about a universe with Kasner. So by Kasner, we made an isotropy, and we dug deep into this to see that what can an anisotropic universe bring to the table. Mostly because it can very well explain the pre-inflationary era or the uh, space-time near singularities and how everything unfolds. So let's have a brief recap of what we know. So say this is the cosmic microwave background image of our universe. For a very long time, not as old as the universe, but the questions that arise to every human being since the beginning of humankind was, how did the universe begin? We were all very interested about that from the very beginning, and so for a very long time, people used to believe that the Big Bang was the beginning and everything followed from there. We had Big Bang, then we had Big Bang nucleosynthesis, we had radiational era, we had matter dominated era, and now we're living in the dark energy dominant era. But something very interesting unfolded when we saw this particular image of the cosmic microwave background. That if you measure the average temperature on this part, and if you measure it on this part, you see that they are in a thermal equilibrium. But given the fact that in the observable universe, we only had causal connection with them in a very recent time. So for them to be in a thermal equivalent state, they had to have a causal connection way before. So something was missing. So in order to find that out, we dug deep and saw that the time when we had the Big Bang nucleosynthesis wasn't. But there had to be something way before that, after the Big Bang, in order for them to be in the causal contact of the galaxies and everything. So what we did is we extended the part over here, and as you can see from the light cones that they intersect and they have a causal contact. So this problem that we face was the horizon problem, and it's one of the key problems in cosmology. So a very good candidate for solving this problem is inflation. So we took the time before the Big Bang nucleosynthesis and the time after Big Bang, and we said that this was the era. So inflation lasted a very small time, as you can see over here. It lasted for only 10 to the power inverse 36 to 10 to the power inverse 32. And it solved the two of the most crucial problems in cosmology, the horizon problem and the flatness problem. So horizon problem said, as I mentioned earlier, the horizon problem said that the universe was in causal contact before the Hubble sphere reached it. So it solved that by saying that there was a point in universe where there was a very short time of expansion, but a very rapid one. And it also solved the flatness problem that we had, which said that the universe was asymptotically flat, as we can see right now. So for a very short period, an exponential growth made the universe flat. So this is the image of inflation. As you can see, there is a slow roll from here going down, and this is the point of Fihi. But there's a big chunk that's still missing over here that we don't know yet, that we couldn't probe yet. We call this kination. It's a part of our rolling scale. So if you look at the chunk that was missing, okay, sorry about that. So from the Big Bang nucleus till now, the time ratio gives us something around 10 to the power 17. But there's still a big chunk missing in between the Big Bang and the nucleosynthesis. Like the point where the inflation ended and the nucleosynthesis started, there was still a big chunk missing, which was of the order 30, which is, as you can see, pretty huge compared to what we have known so far. This is the time from the Big Bang to now, and this is the time ratio in between the inflationary era and the Big Bang synthesis. So, as you know, that the universe that we are in now are homogeneous and isotropic. By homogeneity, I mean that if you take any point in the observable universe, the physics remains the same, and it has translation symmetry. And if you take and by isotropy, I mean if you rotate around in a point, I mean it's rotationally symmetry. So if you throw up in this way and if you throw up in on the other way, both of them will follow the same physics, and that's the universe that we're living in right now. But there are other classifications of the universe that comes down from the Bianchi types, where it can be spatially homogeneous, but anisotropy plays a very important role. And Bianchi type universes are spatially homogeneous, as I said earlier, and also can be anisotropic. So in total, we get 9 of them. And how do we get them? Bianchi types are classified by a 3D Lie algebra, and we have this basis. This is our Lie algebra in our Lie group, which encodes the structure constant. The structure constants give us different types of algebras in the Lie group. So based on the structure constants, as they satisfy the Jacobi identity, we get this the classification of the algebra. But keep in mind, it's up to the change of basis. Meaning, if you change the basis, although a structure constant doesn't look the same, the uh, the although the structure constant doesn't look the same, the coordinate changes. The coordinate changes, but it's still the underlying geometry is still the same. So to avoid that, we take the inequivalent different possible structural constants, and we get 9 types of classifications, where type 1 to 5, 7, and 9 are discrete types. They follow only one algebra. But type 6 and 8, they're families and labeled by a continuous parameter h, meaning they have infinite algebras involved. So after classifying all this, let's look at the Bianchi type 1, which is spatially homogeneous. And as I said, that every Bianchi classification is spatially homogeneous. So to say the universe is spatially homogeneous, 3D flat space, blah, blah, blah. So to see the translation symmetry, I first applied the translation operator TXA and then TYB. So we end up with x plus a, y plus b this. But if we change the order of it, we still get the same thing. So we have translation symmetry. The translations commute. The order doesn't matter. And in a more generative statement, if we take the basis to be partial x, partial y, and partial z, the 3 special bases that we do, we know by inherently that operators, the partial derivative operators, are symmetric. So they commute. And we get this commutation where the basis is commute. And this condition makes the Bianchi type the simplest of the classifications. So a generic Bianchi type metric looks something like this, which has scale factors. And these scale factors define the contraction or the expansion of the space-time in different direction. And if we take all this to be equivalent, A1, A2, A3 equivalent scale factors, we get the Friedman-Lamarck Robertson-Walker metric, or the one we all love, the FLR-Dudley metric, which looks like this. We all know about that. So we get an equal Hubble rate in every direction, and we have isotropy. But what if our universe scales at a different rate? Say our scale factors are not equal. Then we have different Hubble rates in different direction, meaning the universe either expands or contracts, but it's like a blob. You can think of it like a blob where one part goes away from it, another part contracts, or maybe both of them goes out, and we have another part which coming back. So this is an isotrope. We have finally got into an isotrope. And a good example of anisotropy is the Kasner metric. So originally, Kasner metric is a solution to the Einstein's vacuum equation, where it's satisfied by these Kasner conditions, which will look why we get them in the first place. And as you can see over here, we have a summation on the scale factors, which depends on the type of expansion we had. And why do we take the Kasner metric? So Kasner, as I said earlier, the Kasner is a very good candidate in probing into early time universe where there was chaos, the big chaos scenario that in near any singularity, the space-time is locally chaotic, meaning it enters the Kasner epoch, where we have gravitation and we have gravity going crazy, we have quantum fluctuations, and there's lack of thermal equilibrium, so it's a wild and isotropic region. And another reason why we're taking the Kasner is to probe that time right after inflation and before the Big Bang nucleosynthesis, because we are considering that time to have a wild and isotropy because of all the fluctuations and the rolling scale field that you have. So now let's get back to the Kasner conditions that we talked about. So it has two types of conditions. One is the linear constraint and another is the quadratic constraint. The reason we get this is it's just to satisfy the vacuum, to be precisely. So we do the basic GR over here. We get the non-zero Christoffels. Then we work our way through the non-zero Ricci tensors. But the important thing to look over here is that the Kasner is a solution to the Einstein vacuum equation, right? So our Ricci should be zero. So in order for them to be zero over here in the time component, you say that these two has to be equal, and in the spatial components, this has to be equal to 1. And therefore, we get the vacuum equation constraint. So, the Kasner constraint based on the Einstein vacuum equations. Now, what happens if we introduce a higher form gauge field? And one very good example that we all know is the Maxwell. So we introduce a gauge field, a high form gauge field, which takes us away from vacuum because then our energy momentum tensor is non-zero. So because of and from there we're straying away from vacuum, but we still have the Kasner metric working, Kasner-like metric working on delay. So say this is our M form that we introduced, and we get the equation of motion based on this. These are the Maxwell's equation of motion written in differential forms notation. All right, in a more general case, let's take an arbitrary signature, a generic Kasner, where epsilon naught and epsilon I gives us the signature of the metric. Say we have an action where this is the Einstein part, this is our flux part, and we write it in the forms notation. The reason we do the forms notation is to make the calculation much simpler, because we're working with fluxes and everything. It has a much more neater look. So doing basic GR all over again, we vary the action with respect to a potential. And first, we get this equation of motion, which kind of looks like the similar one that we saw earlier. Anyone? The Maxwell's equation of motion. So varying it with respect to the metric gives us this equation of motion. And then we get the non-zero Christoffels and the non-zero Riccis. So now at hand, we have all the necessary information that we need in order to incorporate a flux as a solution to this system. So let's consider a flux ansatz. This is our M-form ansatz that we took. And here I took the exponents to be a summation of Sm and work our way through the basic calculations and everything, and plugging them in our Ricci component. And since our flux over here, we had only the spatial dependence. There was no time dependence. So our first spread goes to 0. We don't have this problem since this is dependent on time. Then we calculate through, let's just plug in the non-zero Riccis that we got, plugging in the equation for the flux we got, we get this. Now, one interesting thing to notice over here is that our Ricci over here scales as 1 over t square. And our flux over here scales as 1 over t square times Sm. So they have to scale in equal footing. And for that reason, we said Sm equals to 1, which is quite similar to the Kasner constraint that we got already. Yeah. So
I was wondering, so you're dealing with the geometric equations, right? The reach tensors and everything, but is there a counterpart to theory because you're using the reach sheets here?
Yeah, I worked out the Chiminu in the trace reverse Einstein equation from where I got this equation motion. In sourcing it with the Yeah, I used the trace reverse Einstein equation where I got the Chiminu. Yes. So we get the constraint, which kind of similar to the Kasner constraint that we got earlier, because this is just a summation of A1, A2 plus A3, right? So now taking the spatial part of it, getting the spatial components in, plugging everything together, we get, including the condition that we got earlier, we get a constant which, as you know, like this A's, the summation of A's has to be equal because there's a constant. And we get another condition where all our exponents are scaling in the same way inside the form. So the I over here are telling me that I'm working within the form. So the I extends from the form to the to M. Now, now we also need to take what's outside of the form. In order to keep consistency with the Einstein equation, you have to incorporate the entire space-time. So working our way through where, since it's outside the form, our form inside goes to zero. So our Fm equals to zero, and we get a similar kind of similar thing, which looks like this, but we still need a constraint for this. So we get a condition for our exponents over here, and taking the ratio, we get a negative sign. The negative sign over here tells us that our exponents on the inside of the form and the outside of the form, they scale at different directions. If one is expanding, the other one is contracting. So from there, moving on, we get another condition for our exponents outside the form. Now, we already have the coefficients for our form for inside the form and outside the form, and we only needed this part, and we get it from putting everything together. We just get a condition for this as well. Now, plugging everything together, we get the field strength constraint, which is this here. Epsilon tells us about the epsilon gives us the sign about the if about the m from kinetic term, and epsilon 0 to epsilon m are just our signatures on the metric. Now, what we saw in the paper by Sabra, that if these conditions are satisfied, then this flux would be a solution to our equations of motion that we got over here. So setting up that constraint, if we have these constraints and they're satisfied, we can solve our system using that flux. A good example for that is the 4D Maxwell. Say it's a 4D Maxwell, so definitely have 1 plus 3 dimension, 1 time 3 space, and gauge potential, which is a 2 form. So plugging those in over here, you get the values for your exponents, and plug everything together in the equation, and taking the 2 form to be special, to be a part of space, where you have the first basis and second basis of the x1 coordinate and the x2 coordinate, and the first two spatial coordinates, and one coordinate would definitely scale in the opposite direction. So we get 2 coordinates in the same direction and another coordinate in the opposite direction. Can someone tell me what this represents? Anyone? It's a very simple thing. We all know about it. This is the polarization of electromagnetism. We know that electricity goes, when electric field goes this way, magnetic field goes that way, right? So we have one polarizing in one direction and the polarizing in the opposite direction. This is just that it's as simple as the electromagnetic wave. Okay. So similarly we get the constraint, the field strength constraint of the 4D Maxwell, to be this, which is far more simpler, which is totally based on the signatures of our metric. So plugging in the metric, we get another condition which looks like this. Now, the field strength magnitude is definitely has to be positive and real, right? So for that reason, our epsilon has to be -1. And this symbol over here, if it's a negative or positive, tells us about our M form kinetic term to be real or phantom. So as you can see, it's -1, so it's phantom. And I haven't really probed much into this, but this seems like a pretty interesting field to explore if you want. Yeah, it talks about negative mass. Okay, so now what happens if we add a scalar field, say a Dirac field? Taking the same methods, we first need to get our constraints right. Then based on that constraints, we need to see if our flux form satisfies the equation, if it's a solution to our system or not. Keep in mind that our metric is still the Kasner metric that we took earlier with arbitrary signatures, which is this one. We're still working with this metric. We just took a different setup. Getting our equation of motion out, we all know what this is, right? Anyone? One of you should know what this is. Okay, he's just playing. So this is the Klein-Cohen equation, and plugging everything in similarly, but in one different thing over here is that we are promoting our phi to be dynamic. So it's dependent on the cosmic time. And with a few calculations, we get another condition for phi with the constants applied and getting the components in a similar way. Oh, it's supposed to be tau. It's a typo. It's a typo. Thank you. Okay, plugging everything in, we end up getting our Kasner dilaton constraint. Now, one interesting thing to look over here that it's quite similar to the Kasner constraint that we had it for vacuum, but extra algebra. So if we didn't have the scalar field to be dynamic, then we wouldn't even have this term in the first place. So this would have been 0, and we would end up with our vacuum Kasner, and our Kasner-like solutions boil down to the Kasner metric for vacuum. So you see that adding the dynamic field over here makes our adds source, and the energy momentum also becomes non-zero, and we stray away from vacuum. So we expect a metric answer like this, where the first part, this is for a d-dimensional field. It's for a d-dimensional field, and this first part is d dimension, and the second part is d minus 1 dimension. Also, d minus d dimension. And this is the non-compact manifold, and this is the part of a compact manifold. The reason why we incorporate this is to solve a few problems that we come about a lot, like the hierarchy problem or some other cosmological problems. And for this metric, we want to solve for we want to work on a system with the metric, the flux, the form, and the phi, and we offer a solution in warped time dependent backgrounds. The reason we yeah,
Like making his mic pick up and I just need to be a bank to compact number.
I'm saying they will get the first. A compact manifold has all the extra dimensions, and non-compact is just the 4D manifold.
But here you have like D dimensions, not four.
D stretches to, and D এর ভিতরে you have 4 dimensions and everything else. So this small d is my 4D.
But what's the rationale for like making this metric?
You mean why are we taking the metric? Yeah. I'm going to go into this. I'm going to go into this. Okay. As you asked, like we're looking for solutions in the warp time dependent background. And the reason why we want warp time dependent backgrounds because it helps us solve different problems in cosmology, like the hierarchy problem, or in and also in particle physics, the hierarchy problem, and cosmology, like brain anti-brain inflation. Say the thing that Walid asked that why we need this metric. If you focus on the first part of the metric, you can see that it's an RS type line, the Randall-Sundrum line. So an RS metric looks something like this. And then another pattern.
Why am I considering the value of this thing? I'll remake my question. This is a very basic question. Why are we considering the exponential work?
Because we're trying to probe the time between inflation and the Big Bang nucleus system. We have a rolling effect, a rolling scalar, right? So the expansion is exponential.
Also, I'm guessing like should be okay. So A and B they don't scale thing, right? Because in D minus D we have more previous hidden there. Chinese Catholic.
There are different functions. Beta is a function of t. Like,
Please. On the top, that is not.
you know the slow roll in inflation, right? So in slow roll we have the kinetic term dominating way less. So in a normal rolling scalar, kinetic term bounces now. Okay, so I think I should write the RS model in neat RS equation in a neat way.
Fundamental phase, right?
Yeah, because we're trying to probe the hierarchy problem where we need the gravitational, the graviton coupling, like the graviton and the essential left to scale in the centimeter.
I'm not sure. Actually, let me tell you if you want to answer them on this. In this plasma theory, what is the corresponding gauge group that it satisfies? If this gauge group is a product group, can we come up with subgroups as effective features? Can we extend this gauge group to a gauge monoid?
I'm not sure if H mono is. I don't think I've sunk my teeth in that deep into the question, but I think I think it's going to be a bit premature of me to make a bold comment like that, as I'm still on processing. I'm still in the basement of this entire project. So Kasner has many possibilities. Many possibilities. It incorporates anisotropy, and I mean, if you try to, I think if you look into it, I think you can get something. But I'm not sure about it. I need to do a little bit more studying on this. Alright. So the Brownlow syndrome, the RS1 metric, where we have the phi term over here, which is our compactified dimension, and we have the 4D dimensions over here. So what happens in this scenario is that phi has 2 points with 3 branes. So what RS1 does is to solve tries to solve the hierarchy problem by incorporating 3 branes at phi equals to 0 and phi equals to pi. and in between we have the bulk. So similar to that, you can use this part as a motivation for a similar RS scenario where we can attempt to solve particle physics problems like hard. And the motivation regarding having the second term over here is scale separation. A much more detailed version of it is given in Valriet's paper. I added these in reference. So what we do with scale separation is that we get the scale factor of the 4D to be much, much less than the Kazi line. Meaning if you now work with the 4D, the Kazi line is way above and you can ignore the entire Kazi line tower and work in the 4D physics and a high dimensional theory of the scale separation, if there is scale separation. And the reason why we're trying to find a time-dependent solution using the warp time-dependent background is because our universe has a history of time dependence. Say it was the say it's today the dark energy domination, or say it be inflation or matter domination. We uh, we always had the time dependence in our recorded history. So this seems like a very plausible way to move forward and try to probe into that part of that time part, the 10 to the power 30, where inflation ended and the Big Bang nuclear synthesis started. And a very good candidate could be kination with the rolling scale field. Then, as always, thank you to Ahmed Rakin Kamal sir, Dr. and Dr. Ratu Hanta sir for their unwavering support all the time. And definitely I couldn't have done it without my collaborators, Walid and Fahim. So if you guys want, I'll attach this file with the post and check out this paper by Van Rier regarding scale separation. It's very nice. And if you guys want to dig deep into Bianchi universes, this is good as well. And we worked on this paper and most of the calculus are from there.